This is SpaceTime, Series 26, Episode 127, for broadcast on the 23rd of October, 2023. Coming up on SpaceTime, astronomers discover newborn galaxies. The Psyche mission finally blasts off, bound for a metal asteroid. And the Americas mesmerized by an annular eclipse. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers are now able to look so far back in time, they are quite literally witnessing the very birth of galaxies. Throughout most of the history of the universe, galaxies seemingly tend to follow a tight relationship between how many stars they've formed and how many heavy elements they've formed. But now, for the first time, astronomers are seeing signs that this relationship between the amount of stars and elements does not hold true for the very earliest galaxies. A report in the journal Nature Astronomy suggests the reason is likely to be that these very early galaxies are quite literally still in the process of being created, and so they simply haven't had the time to create any of the heavy elements. The universe is teeming with galaxies, immense collections of stars and gas, and as we peer deep into the cosmos, we're seeing them near and far. Because the light has spent so much time reaching us, the further away a galaxy is, we essentially are looking back in time, thereby allowing us to construct a visual narrative of their evolution through cosmic history. Observations have shown that galaxies through the last 12 billion years, that is 5/6 the age of the universe, have been living their life in a form of equilibrium. There appears to be a fundamental tight relationship between, on the one hand, how many stars they've formed, and on the other, how many heavy elements they've formed. Now, in this context, heavy elements means everything heavier than hydrogen and helium, and astronomers refer to these elements as metals. Now, this relationship makes a lot of sense, because originally the universe only consisted of primarily hydrogen and helium, the two lightest elements. All the heavier elements, such as carbon, oxygen and iron, were created later by stars, either during their lives or when they died. The very first galaxy should therefore be unpolluted by heavy elements. But until recently, astronomers haven't been able to look that far back in time. In addition to being further away, the reason is that the longer light has to travel through space, the redder it becomes, because space itself tends to stretch out and expand. And that means everything in it is doing the same thing, including light waves. And for the most distant galaxies, you have to look all the way back into the infrared part of the spectrum. And only with the recent launch of the Webb Space Telescope have astronomers been able to do this. And the vistas that Webb have shown us so far have not disappointed. The Infrared Space Telescope has repeatedly broken its own record for finding the most distant galaxy. And now it finally seems that we're reaching an epoch in space-time where the very first galaxies were created. This is just a few 100 million years after the Big Bang itself. This new study has discovered what seems to be some of the very first galaxies which are still in the process of being formed, and it's helping to change our understanding of the universe. Astronomers have always been looking for the relationship between total stellar mass of a galaxy and the amount of heavy elements it contains. Usually the more massive a galaxy, the more heavy elements it has. But this relationship is now being challenged by these new observations. When they analysed the light from 16 of these early galaxies, astronomers saw that they had significantly less heavy elements compared to what you'd expect to find in terms of stellar mass and the amount of new stars they produced. In fact, the galaxies turned out to have, on average, 4 times less heavy elements than later in the universe. The results are in stark contrast to the current model, where galaxies evolve in a form of equilibrium throughout most of the history of the universe. Mind you, this result is not entirely surprising. Theoretical models of galaxy formation based on detailed computer programs do predict something similar, but this is the first time we've actually seen it. The explanation as proposed by the authors is simply that what we're witnessing are galaxies being created. Gravity has already created the first lumps of gas together, and this gas has collapsed to form the first stars. If the galaxies then lived their lives undisturbed, the stars would quickly enrich them with heavy elements. But in between the galaxies at that time were large amounts of fresh unpolluted gas streaming down onto the galaxies literally faster than stars can keep up. One of the study's authors, Claudia Lagos from the University of Western Australia, says the results provide the first insights into the earliest stages of galaxy formation, which appear to be more intimately connected with the gas between the galaxies than previously thought.
Until basically right before the JWST was available, we couldn't really see galaxies in that first billion years of evolution, or we could see very extreme galaxies. So I guess the hope was always that the JWST would be able to see the more normal galaxies around those extremely early times of the universe. So just for reference, we think the universe is about 14 billion years old, so we're talking about that first one. So it really was trying to push to get to a view of the normal galaxies around that time. And that's what a lot of people have been doing this first year of JWST data.
When you look around here, there are some ellipticals, but the spiral galaxy, such as the Milky Way, that seems to be the pretty standard cookie cutter that we see.
Yeah, that's right. So in the as you say, in the what we call the local universe, those are typical galaxies. So you have the most massive ones. These are very rare. And similarly, in the very early universe, you have extremely bright galaxies that are very rare. So we always wonder what happens when you start to get to the more numerous galaxies. How would they look like? And that's the question we're trying to address here.
You guys aren't just talking about the shape of the galaxy. You're also talking about its metallicity, the chemicals that make up the stars in those galaxies.
Yeah, that's right. So one of the things that has been quite extraordinary is that we observe these relationships between galaxy properties in the local universe that seems to hold even, 10, 12 billion years in the past. So if we look at, in this case, we're looking at the amount of stars in galaxies, the rate in which they're forming stars, and the amount of, or the chemical composition of the galaxies. And we see these three properties are very strongly correlated in the local universe. And it just turns out that as far as we could look before the JWST, all the galaxies seem to follow the same relationship. So that's how it became to be known as a fundamental relation of galaxies. But it turns out that these very early galaxies do not follow that same relationship, which it's surprising, and not so much in the sense that it's a very extraordinary time for the formation of galaxies, where a lot of them are forming perhaps their first or second generation of stars. So I think it was incredibly exciting to see that when you go so early, these relationships they start to break. It's not surprising, but we didn't really know. And also in which way they start to break is very interesting.
So we have stars forming in the early universe, and different types of stars die at different rates, and
that's right.
And they have different chemical compositions when they reach their end. Stars 8 times or more the size of our sun, the mass of our sun, I should say, they can grow really big and really massive, and they can even be producing iron in their core before they explode as supernovae. When they do this, they then seed the universe with that iron, and that becomes part of the next generation of stars. And as that cycle repeats itself with all these different elements from oxygen and carbon through to iron, then gradually you'll see a steady increase in what we call the metallicity of these galaxies because of that evolution.
Yeah, exactly.
You're saying that with the very earliest stars and galaxies, that curvature, that graph isn't the way it should be.
Yeah, that's very much the main conclusion. And in fact, because this, as I was saying, we have these three properties that are strongly correlated in galaxies, that a lot of that is coming down to how galaxies, or the average galaxy, is growing, and we call that they're growing in some sort of equilibrium where there are different processes that are balancing each other to give you this beautiful correlation. But what we think is happening is that very early on in the universe, there's no balance between these different physical processes, and for that I mean how quickly a galaxy is gaining gas from around itself, how quickly you form stars out of that that gas. And then similarly, as you say, how quickly some of those stars return elements back into the interstellar medium, which would be the gas inside the galaxy. So all these processes are clearly not balancing each other in the way we see later on, and all the way down to our local universe, which we see still very much are in a good balance. It's not necessarily crazy to think that balance is broken because of how much is going on early on. There's a lot of gas around galaxies. A lot of that is already cold gas for, standards in astronomy, I suppose. So it's quite easy to form stars out of that gas. We think that gas is also what we call pristine. So there's no metals in that gas. It's pretty much just helium and hydrogen. So that seems to be breaking some of these balance.
So what we're really seeing here is the influence that the very first those population 3 stars would have had.
Yeah. That's right. Whether they can reach far enough into affecting, for example, galaxies nearby them or not. Or, for example, they're able to just pollute their most immediate medium. And that's the kind of thing that would make a difference here. So a lot of these galaxies could have, as I said, they'd be on the first, second, or just third generation of the stars being formed. So I think it's very exciting because we're seeing kind of a convolution of all these processes and how they differ from what we think they look like further in the future, if you want, so closer to the current time.
What's the difference in the metallicity you're seeing with these stars compared to what we see in the universe around us, or for that matter, for the 12 billion years since then?
So what we're seeing is these galaxies are about 3 to 5 times less what we call metal rich than they should be. So they have about 3 to 5 times less oxygen than we were expecting them to have based on these relationships that we see over the last 12 billion years. So it's a big difference. It's quite significant. And even though the sample we have, it's a bit less than 20 galaxies, it's not huge. So hopefully we start to get more and more data to make this a very solid result. It's very significant. So the difference is large enough that even with this small sample is significant.
What we're seeing a big step before we reach the curve. The metallicity on stars appears to follow a standard trend.
Yes, that's right. So you're seeing in the roughly a billion years later, it looks like all galaxies are back on track, if you want, in this relationship. So it's a very, it's a fast transition.
And this corresponds to the epoch of reionization that you're looking into, isn't it?
Yes, that's right. We're right into that, yeah.
That's an important time in the universe's existence.
Yeah, that's the first time, the closest to us, if you want, where we see a full change on the ionization of the gas in the universe. So we're going from a universe that is completely neutral, so all atoms are in the neutral form, to pretty much everything being ionized after this, what we call reionization.
So before that, there weren't any stars, so to speak.
That's right.
And then the stars started ionizing the universe through ultraviolet radiation, affecting the hydrogen. So instead of it being opaque, it becomes clear, and we have the universe which we see today.
Exactly. That's exactly right. So all that transition happens around that first billion years. So it is obviously connected with how this process is going on, this reionization is happening.
With the James Webb Space Telescope, one of the big hopes is that we will see one of these very first population 3 stars, the stars formed out of the pristine gas of the Big Bang. Are we getting close to that yet?
That's a great question. This is one of the main hopes for the JWST. We haven't yet detected that, but I think the hope in the community, and we've done polls of this, I think people are expecting to see that in the next 5 years. So it could happen anytime, because sometimes some of these things are luck, right? Whether you happen to see the right, be at the right time in the right place, more or less. But the hope is that, yes, it's achievable, and we should be able to see that. They're very bright. I mean, still need a massive space telescope to see them, but the hope is that they're bright enough that we can start to see the first one in the coming years, I guess
the big question is we don't really know what to look. I mean, we have a rough idea what to look like spectrally wise, but we don't really know what they're going to be, whether they're going to be small or... the big theory is there'll be huge, massive things 200 times the size of the sun, but we don't really know. That's
actually true. So we think, theoretically, we expect them to be a lot more massive than the sun, just because generally to reach that very small masses for stars, you need actually metals. So you need all these extra elements that you were describing earlier, like carbon, oxygen, etc. and we don't expect that to be present, right? So the theory is that these stars could be much more massive, but you're right, it could be, maybe 50 times the sun's mass, or it could be, 200 times, and maybe that's the type of, difference that will make it possible to discover it in the next year versus maybe 5 or so years. So you're right. I mean, this is going to be a big surprise for sure, and it's the kind of thing that will really help us build a much more solid understanding of how stars form, especially these very early stars.
The bigger a star gets, the quicker it goes through its fuel supply. When you're talking about really massive stars, they don't live long. They're the James Deans of the astronomy world, as we like to say.
That's right.
Is that a problem, the fact that you're looking for stars which aren't going to be around for a long time anyway?
Yes. That's part of the problem, because that makes it, you need many of these, basically. You need many of these to have a chance of seeing it, right? So the fact that they're short-lived makes it a bit more difficult. But hopefully, because there's continuous scanning over different parts of the sky, that will make it possible. But you're right. If we had a James WST with a very wide field of view, so that means that sampling a large fraction of the sky every time, that would make it a lot easier, because then you're in a much larger proportion, right?
Well, they're building that now, aren't they?
Yeah, exactly. So if it's not the JWST, it's probably going to be the next generation Rubin or other space telescopes. But there is a lot of hope and justified hope that this should happen with the JWST.
Where to next?
Yeah, so the hope now is to start building large samples of galaxies around this epoch of reionization. So we are now on the dozens, but we want to get to thousands in the next year or so. And that's where we're heading. It's definitely going to happen in about a year or so. So it's exciting times.
Before James Webb, the standard view, based on what we could see through Hubble, was that earlier galaxies looked very much like train wrecks.
Yes.
Now as we're seeing these new images, that vision is disappearing, isn't it?
Yeah, absolutely. And that's not necessarily unexpected. Even if you look at galaxies nearby and you look at them in ultraviolet, which is what the HST is looking at, these very early galaxies, they look very regular. They look like train wrecks, as you were saying. But we know that as soon as you look at in the optical or the near infrared, they look pretty regular galaxies. And that's basically what we're starting to see here, that a lot of them don't look like train wrecks, even though these are extremely early galaxies. So it's nice to see that for sure.
That's Claudia Lagos from the University of Western Australia. And this is SpaceTime. Still to come, NASA's Psyche mission finally blasts off bound for the asteroid Psyche, and the Americas are mesmerized by a spectacular annular eclipse. All that and more still to come on SpaceTime. NASA's Psyche spacecraft is finally on its way, undertaking a 6-year, 3.6 billion kilometre voyage to a mysterious metal-rich asteroid, which could hold secrets about the formation of planets like the Earth. Psyche successfully launched aboard a SpaceX Falcon Heavy rocket from Launch Complex 39A at the Kennedy Space Center in Florida.
Falcon Heavy is in startup.
Good call out that the Falcon Heavy is in startup. Now we're going to get the go at T-minus 45 seconds.
Go for launch.
We are go for launch. All systems are go to send the Psyche spacecraft to deep space. And here we go with the final seconds of launch. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Engine ignition. And liftoff. Liftoff of Falcon Heavy and Psyche on a mission to a metal asteroid in deep space to study the building blocks of our planet's inner space.
Vehicles pitching downrange.
M1D chamber pressure is nominal. Power and telemetry nominal.
Power telemetry nominal. We're also looking at the data for all 27 engines.
Falcon is supersonic.
All chamber pressures look good, and Falcon is supersonic now.
Throttling down in preparation for Max Q.
What will happen here
Max Q.
The side boosters will be at full power, and the center core will be at a reduced power to go through Max Q to reduce the pressures on the structure of the launch vehicle.
Coming up in 30 seconds, we'll start getting ready to have those boosters cut off.
Vehicle's looking good, pitching down range. All telemetry looks really good so far. Data is looking really good.
All 27 engines of the Falcon Heavy putting down 5.1 million pounds of thrust. Standing by now for booster engine cutoff for those side boosters. The center core booster will continue on.
Booster engine cutoff. Side booster separation confirmed.
Side boosters coming off the rocket.
MVAC engine chill has started.
And there we start the chill on stage 2 as we get ready for MECO on the center core. Stage 2 will continue chilling down, making sure the fuel and propellants are flowing through that MVAC, getting ready for ignition.
Those boosters will have 3 burns, 2 re-entry burns and 1 final landing burn before it comes back down at LZ1 and LZ2, landing zone 1 and 2 here at the Cape. Next up is main engine cutoff of that center booster. After that cuts off, there'll be a series of steps that will happen in close succession. Main engine cutoff, the center core stage will separate, and then we'll start the second stage burn, the first of 2 burns today.
That was a shutdown.
Looking
main
now
engine
inside
cutoff.
The booster. There you have MECO.
Stage separation confirmed.
And there it goes. The second stage lighting up its
MVAC
MVAC
ignition.
engine.
Center core FTS is saved. Bermuda.
Calling out the communication stations.
Bearing separation confirmed.
Boostback has been completed, and they're in extended coast right now.
And there go the fairings. Revealing Psyche, the fairing falling away back to Earth. SpaceX has their recovery vessel.
Vehicle is on a nominal trajectory.
Their recovery vessel, Bob, is out in the waters right now, looking to recover both of them. Getting a good burn now from the second stage. This lasts about 4 minutes. We are going out over the Atlantic Ocean, heading south towards southern Africa. The glowing engine of the stage 2.
Yeah, we should see in about 20 seconds, we should see the booster entry burn, which would be the 1 engine on both side boosters. Yeah, all the data so far, telemetry is looking nominal. I see the telemetry chilling down the engines for that booster entry burn on the side boosters, starting up in the telemetry. Everything's looking nominal. The vehicle second stage is performing very well, and side boosters are coming back.
Boosters entry burn startup.
And there we just heard booster entry burn startup is happening, and on the side boosters.
Boosters entry burn shutdown.
Booster entry burn on 1 and shutdown. Booster entry burn on the second side booster and shutdown.
Next burn is the final landing burn. And for
PYNY FTS is saved.
And for folks who are in the area, you end up hearing that loud sonic boom, that thunderclap, just about the time they make landing.
Stage 2 is on a nominal trajectory.
You and I here at Hangar AE, just a couple of miles away from this landing zone, we certainly hear it and feel it.
Yep, and I see now that the side boosters are supersonic, transitioning to transonic. Landing burn has started.
Terminal guidance.
Here it comes.
I don't know, Daryl, but that sonic boom was great for us. I'm sure Jim is excited over there. There's the second one. I'm sure the host desk over there is feeling that really well.
Literally, our monitors were shaking as both those boosters broke the sound barrier.
And we just heard booster landing confirmed as both landing zone 1 and 2. Everything looks great. And then the call out for
Stage 2 FTS is safe.
Seco 1, stage 2 engine cutoff. So Daryl, this will put us into that 45-minute coast, allowing us to do
nominal
that
park
barbecue
orbit
roll.
insertion.
The 2 side boosters on their landing pads, coming down more staggered than I'd seen them before, but nonetheless, perfect landings for them both.
About an hour after launch, the spacecraft separated from the upper stage of its launch vehicle and established two-way communications with NASA's Deep Space Network complex in Canberra, telling Mission Control that it's in good health. Getting here has been a long, drawn-out process for the Psyche mission. The project suffered a number of delays, which have pushed the mission back by over a year. The spacecraft missed its original launch date of August 2022 because of software testing problems, and the COVID-19 pandemic didn't help either. More recently, the mission suffered another delay, this one for just over a week, in order to give engineers more time to verify parameters used for nitrogen cold gas thrusters that orient the spacecraft. Those parameters required changes after the engineers concluded that the thrusters would be operating at warmer temperatures than previously predicted. See, operating the thrusters within temperature limits is essential in order to ensure the long-term health of the units. The verification work involved running simulations and making adjustments to flight parameters and procedures. Still, it's up there and flying nominally now. And by August 2029, the spacecraft will begin to orbit the 279-kilometre wide asteroid Psyche, the only metal-class asteroid ever to be explored. Integrated onto the spacecraft is NASA's Deep Space Optical Communications Technology Demonstration, a test of deep space laser communication systems that could support future exploration missions by providing more bandwidth to transmit data than traditional radio frequency communications. The first opportunity to power on the optical communications technology demonstration is expected in about 3 weeks' time, by which point Psyche will be roughly 7.5 million kilometres from the Earth. This will be the agency's first test of a laser communication system beyond the Moon. While the transceiver is hosted aboard Psyche, the tech demo won't actually be relaying Psyche mission data. But if it works, you can expect to see it in more missions in the future. Asteroid Psyche is located in the main asteroid belt between Mars and Jupiter. Its high iron-nickel metal content led astronomers to think that it may be the partial core of a planetesimal, a building block of an early planet. 16 Psyche is a large M-type metallic asteroid. It was discovered on the 17th of March 1852, and it's named after the goddess Psyche, one of the most celebrated characters of Greek mythology. She was known as the goddess of the soul. In fact, her name means breath of life, and she was linked closely to the inner human world. Her beauty is said to have rivaled that of Aphrodite, the goddess of love. As for the prefix 16, that simply signifies that it was the 16th minor planet to be discovered. Psyche is the largest and most massive of the M-type asteroids, and one of the dozen most massive asteroids known. In fact, it contains about 1% of the total mass of the entire main asteroid belt. Historically, it was always hypothesized that Psyche was an exposed metallic core, probably resulting from a collision with another body that stripped away the crust and mantle of the original larger differentiated parent body, which would have been around 500 kilometers in diameter. A second hypothesis is that Psyche was disrupted and then gravitationally reaccreted into a mix of metal and silicate. In this case, it may be a candidate for the parent body of a class of stony iron meteorites. The latest hypothesis is that Psyche may be a differentiated object, like Ceres or Vesta, but it experienced ferrovolcanism while cooling. Now, if true, this model predicts that the metal would be highly enriched only in those regions containing relic volcanic centers. And it's this third hypothesis which has been bolstered by recent radio observations of the asteroid. Psyche principal investigator Lindy Elkins-Tanton from Arizona State University says the mission will be undertaking a 26-month science investigation of what really is a very different kind of world in our solar system. As for the first 100 days of the flight getting towards Psyche, well, that's a commissioning phase called the initial checkout period to make sure the flight systems are healthy. Key to the checkout is ensuring that the electric thrusters are ready to begin continuous firing for long stretches of the journey. There's also active checkout of the science instruments, the magnetometer, the gamma-ray and neutron spectrometer, and the multispectral imager. That'll start in about 6 weeks' time. Now, during this period, the imager will make the first images for calibration purposes, targeting standard stars and a star cluster at a variety of different exposures with several different filters. Then, the Psyche team will activate an automatic feed of publicly viewable raw images online, and that'll keep going for the whole duration of the mission. This report from NASA TV.
It's a shame, but living in the city, very rarely do you get to see stars.
I feel like I have a new connection to them in a way that I haven't before.
If I'm out in the desert and I look up at the sky, you just see millions and millions of places that we should be going.
It's almost baked into our DNA, the desire to go and explore, right? That's the whole reason why we left the forest and then traveled across oceans just to see what's out there.
I was born in 1969, which is the year we landed on the moon. So I am a space baby.
When I was a kid, there were guys driving cars on the moon. They're driving cars on the moon. That's so cool, right? I want to do that.
All the rocky planets that we know of all have got a metal core in their center. And especially for the Earth, it's the source of our magnetic field. But we don't know a lot about our core. What we've learned about it, we learn indirectly because we can't go there.
It's too hot. The pressure's too high. Our instruments would melt. Can't drill a hole that deep in the Earth or other planets. It turns out we can study a planetary core out in space because there's this one object. It's one object called Psyche.
16 Psyche is an asteroid that orbits the sun out between Mars and Jupiter.
It is the only asteroid that we're aware of that is 95% metal or more and is really huge. It's about 200 kilometers across in one axis.
So it's about the size of Massachusetts.
It's believed that it may be a remnant core of an early planetesimal that was formed in the very, very earliest parts of the formation of the solar system.
And after this planet started forming and this metal core formed inside of that, it collided with other bodies that then stripped off the rocky mantle, leaving this core in place.
The first thing that came actually was the theory. Some people from Jet Propulsion Laboratory contacted me and said, we would like to plan a mission that would test your hypotheses.
And that starts you down a road that takes years. So we wrote a proposal to send a NASA spacecraft to visit this big ball of metal. And then Lindy gets a phone call. You win. And then we're all like, oh my God, now we have to do it.
Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And it would be the first metal object that humankind has ever visited.
We've been approved to go, so we talked with our mission design and navigation team, and in fact, they were able to come up with what is probably the most optimal trajectory, doing a Mars flyby.
Flies past Mars, gives us a gravity assist, uses that propulsion system to then slowly creep up.
SSL is building the solar electric propulsion chassis. When we do the mechanical, physical integration of each instrument on the spacecraft, we'll work hand in hand with each of the providers to get out to Psyche and do a full discovery mission.
We've figured out a way for many, many people to build something together so complicated, no one person can understand it, but it all has to work together perfectly for decades without fail.
Just the fact that these things work at all is a thrill. It's just a testament to the engineers at JPL and the companies that we collaborate with that they can build these things.
It's exciting for me to be able to be a woman winning and leading a deep space mission. The only previous woman who competed, won, and led a deep space mission was Maria Zuber, who was my friend and mentor at MIT. And so my drive is to make everyone feel welcome and to have every voice heard. We want as many undergraduates as we can. We want to involve as much of the public as we can. We want people to feel like this is their mission.
You get that first picture back, and one of the first things that goes through your mind is, oh, thank God I didn't leave the lens cap on. We will put our pictures out there as soon as they come down. So we'll discover at the same time that the public discovers. We'll be scratching our heads and it's like, I don't know what's going on. At the same time, everybody else is like, wow, what is that? I don't know, let's figure it out.
I did get to look at Psyche through an optical telescope in my backyard. Some wonderful colleagues brought over their telescope on a fortuitous night. It's a very, very tiny, faint dot. And that made a bunch of us cry to think that we could send something to investigate that speck of light.
We can understand this universe that we live in. We can explore it, we can learn about it, and we can be a part of something which is much bigger than just us or just this planet. We will see new things when we visit a world made of metal.
And in that report from NASA TV, we heard from Psyche Principal Investigator Lindy Elkins-Tanton from Arizona State University, Psyche Deputy Principal Investigator and Imager Instrument Lead Jim Bell, also from Arizona State. From NASA's Jet Propulsion Laboratory in Pasadena, California, we heard from Psyche Deputy Project Systems Engineer Tracy Drain, Psyche Project Systems Engineer David O, and Psyche Project Manager Henry Stone. And from Space Systems Laurel, we heard from Chassis Program Manager Steve Scott. This is SpaceTime. Still to come, An annular eclipse mesmerizes the Americas, and later in the science report, new studies show that some 20% of Australian teenagers are vaping. All that and more still to come on SpaceTime. On October 14 this year, the moon aligned perfectly with the sun and the earth to produce an annular solar eclipse. The spectacle bathed millions of Americans in a lunar shadow as the moon blocked out most of the sun's rays. An annular eclipse occurs when the moon passes in front of the sun but is too far from the earth to completely obscure it. That only happens in a total eclipse. See, the moon's orbit around the earth isn't completely circular, it's slightly elongated. And so there are times when the moon's a bit closer to the Earth, perigee, and times when it's a bit further away, apogee. And when the moon is at or near its furthest distance from the Earth, apogee, during an eclipse, it becomes an annular eclipse. Now, if the lineup's perfect, it leaves the sun's edges exposed in a red-orange ring, often referred to as the Ring of Fire. As well as people on the ground, the celestial wonder was also observed by NASA's EPIC, or Earth Polychromatic Imaging Camera, aboard the Deep Space Climate Observatory spacecraft, a joint NASA, NOAA and US Air Force satellite. This sensor provides frequent global views of the Earth from its position in Lagrangian L1 point. That's a gravitational well where the forces of the Earth and Sun balance each other out, located about 1.5 million kilometres from the Earth's surface. The spectacular observations showed a ghostly dark shadow falling across the western United States starting in Oregon, although cloudy skies blocked out the view for some sky watchers. The path of annularity, and yes, that's how it's said, then moved southeast across Nevada, Utah, Arizona, Colorado and New Mexico, before finally passing over Texas and then out over the Gulf of Mexico near Corpus Christi. The annular eclipse was also partially visible across Mexico and countries in Central and South America. For those on the annular path, the times of maximum annularity range from a few seconds at the outer edge to a maximum of around 4.5 minutes at the center of the path. The next annular solar eclipse visible from the United States won't occur until the 21st of June 2039. But there will be a total solar eclipse to darken America's skies from Texas to Maine on Monday, April the 8th next year. We'll keep you informed. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. Well, despite all the health warnings and confirmed links to cancer, a new study has found that 20% of Australian teenagers are now vaping. The findings, reported in the Medical Journal of Australia, calls for urgent efforts to reduce the uptake and use of e-cigarettes among teens. The study, which is one of the largest surveys of Australian adolescent e-cigarette use ever undertaken, found that a fifth of young people had vaped in the past 12 months. The authors surveyed 4,204 high school students from 70 schools across New South Wales, Queensland and Western Australia. They found that 26% of respondents had used e-cigarettes, with the average age of first use being 14. The survey also found that the prevalence of use over the past 12 months was higher for boys and non-binary participants than for girls. The authors are calling for a multi-level approach through policy, investment in prevention and cessation support, as well as communication campaigns in order to tackle the problem. Scientists are warning that the family of diabetes drugs, including Ozempic, are associated with an increased risk of gastrointestinal issues. A report in the Journal of the American Medical Association used information from a health database to compare potential side effects of glucagon-like peptide-1 agonists like liraglutide and semaglutide, which is Ozempic, with bupropion naltrexone, or Contrave, another obesity medication. The researchers say semaglutide and liraglutide were associated with increased risks of pancreatitis, gastroparesis, and bowel obstruction. A new study shows that the likelihood of hailstorms has dropped dramatically across most parts of Australia over the last 4 decades. Understanding how hailstorm frequency has changed over time will help emergency services build resilience against future hail events. By studying atmospheric patterns across Australia over the past 40 years, scientists from the University of New South Wales and the Bureau of Meteorology have discovered that the number of hail-prone days has decreased across much of Australia, but amazingly it's actually increased up to approximately 40% in some heavily populated areas. The study, reported in the journal Nature, represents the first continental-scale analysis of hail hazard frequency trends across Australia. Researchers say that not just any thunderstorm can produce hail. Hailstorms require certain atmospheric ingredients in order to form. One of the important ingredients is that the atmosphere needs to be unstable. This means there's a propensity for updrafts to form. Updrafts occur when there's warm air near the ground and cooler air further up. And if a little bit of that warmer air gets into the cooler air, then it rises like a balloon and it draws more air into the updraft. There also needs to be enough moisture in the updraft for there to be suspended liquid water and ice all swirling around high up in the storm. Another factor is that hail melts as it falls, and so even if you have hail forming up high, it has to be large enough to survive melting to actually reach the ground as a block of ice. And finally, hail formation is enhanced by wind shear, the changing properties of wind by height. That is, the wind changes direction or velocity as you get higher in the atmosphere. If there's a lot of wind shear, then the storm tends to be more severe and more prone to forming hail. When all these factors are present, the atmospheric conditions become hail-prone. A new study has suggested that in some fields, at least a quarter of clinical trials might be problematic or even entirely made up. Tim Mendham from Australian Skeptics says it shows a serious problem with the current peer review method.
The issue of learned papers, scientific papers, how accurate they are has been not acknowledged for a long time. It's always been seen as an issue, and people have been investigating it. The trouble is what happens with especially clinical trials, medical trials is probably the big area they're looking at, is that when a paper is submitted, it goes to a supposedly learned person who says, yeah, this is okay, publish it. But half the time the learned person doesn't have a lot of time to look through all the papers, really. They're doing their other work of being a researcher/educator, and they are philosophically obliged to actually look at other papers and things. That's part of the professionalism of being a scientist. But they might just look at it and say, yeah, it's got the right spelling and it's in the right format, etc., and it looks okay from a quick view. And that's peer review. But the real peer review comes from when it's been published, and people can then, the general public, not the general public, the whole profession can then look at it and assess the evidence, and that's where the real judgment.
It's not a case, therefore, of actually repeating the experiment to prove it's right.
Well, it should be. I mean, that's what they say. To replicate an experiment and find out if it's true or not would only happen in high-profile experiments. Yeah, someone comes along with a little study of how many people hurt themselves when they fall over a stone. Not many people are going to replicate it. It's not really worthwhile doing. A big issue, which is like overturning science as we know it, is obviously going to get a lot of replication. The trouble is there's citations where people refer to a paper as if it's 100% true, and that is the problem, because what happens then is that the people doing the meta-studies, groups like Cochrane, who look at all the studies on a particular field and basically average out the results to see if there's anything there, the ones that are negative results, the ones that are positive results, to see where the median lies, or the mean, to see if it's worthwhile pursuing. The trouble is, if they're including in there a lot of negative or poor papers, or even fraudulent papers, then that means their judgment is skewed. And the question is, how many of these might be fraudulent or negative? And that requires a lot of work, obviously, going into the papers. What they found, what some particular study did of, I think he looked at 500 studies over a 3-year period in medical research. He asked for the detailed results, the data. He didn't get it all the time for various reasons, but he did get it for about 150, and he looked at those data and sort of worked out if they were correct, and he sort of judged that in about 44% of the time they contained at least some flawed data, which he sort of describes as impossible statistics, incorrect calculations, or duplicated numbers or figures. And of course, there's also the issue of fraud. People make up numbers and data. They even make up entire tests.
And they can be influenced to go a certain way in their results. We saw that we won't go into that now, but they can be influenced by their superiors to write a paper to provide a certain outcome?
There's various aspects. One is a publish or perish, that you need to have put out a lot of papers to keep your job at a university, say, and to keep your reputation up. But also, yes, there is the pressure to come up with a certain result. And the institutions themselves, apart from that we want a particular result because our sponsor is sort of keen to have that answer, is that also that the institutions love a lot of papers being published. It's good for their reputation. The trouble is this 44% was about studies where they could get the detailed data, not names of people, but the detailed data, the numbers. When they couldn't get that, they found that it was only aggregated data. They found that only about 1% had no substance at all and 2% had flawed data. So in other words, when they could get the data, they found a lot of problems. When they couldn't get the data, there were no problems with the data, which sort of is a no-brainer, really. And they're looking at other people doing the same sort of thing in other areas apart from the area they were in, and they're finding the same thing. A classic case recently is, I think it came out of South America, some studies about ivermectin being useful in the treatment of COVID. And I know people personally who were looking into that, and they found out that the trials that they quoted had actually never been done, let alone that the data was wrong. It was made up. There was no evidence of these trials ever actually being done. So people were just faking information. People often fake information by copying someone else's and saying it's theirs, and other people just totally make it up, make up the false clinical results. They claim how many people we tested, blah, 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 when they didn't do any of it. And that was the case certainly with some of the trials on ivermectin. So the reliance on scientific papers as absolute accuracy is wrong, and that means that the reliance on the people who do the meta-studies, where they look across a whole range of, a wide number of these studies and then get an average, and that's heavily relied on by people who can't afford to read every paper. They rely on these averages, and they might be totally skewed by incorrect and false results. So it's very much a big problem.
It's a huge problem because peer review is all we've got. I mean, that's it. That's how you know that if it's not peer reviewed, it didn't happen. That's been the mantra for years.
That's why you need to go beyond the initial peer review who says this paper can be published to then looking at it when it's thrown out there beyond being the beta test, the real thing, put it in the wider arena and see if people say, hang on, that's junk. It's a good thing that they have been found.
That's Tim Mindham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.